Hey guys, in this lesson we would discuss Ka, percent dissociation, and pH as well as its applications. Let's first understand what is meant by the term Ka. We already know uppercase K is used for equilibrium constant. However, when we see the small a subscript with K, that means equilibrium constant for the ionization of an acid. Now, acids are always two types. One is strong acids and one is weak acids. If we consider an example of a strong acid such as HCl, HCl would completely break off to give us H positive plus Cl negative. This is called dissociation of an acid. Because it's a strong acid, so this is the dissociation of a strong acid. However, technically this reaction is possible if we dissolve this acid in water. Because water is taken in excess, that's why we do not mention it here. And if that is the case, H positive would be written as hydronium ion concentration, because this H is going to be given off to H2O and Cl is left alone. So this is how the exact reaction looks like. Now, if we are talking about a strong acid, the acid is going to completely give off hydronium ion concentration because this acid is going to dissociate completely. That means it's going to break up 100%. Therefore, we would say its percent dissociation is approximately 100%. Whereas, if we talk about a weak acid now, let's say we have a weak acid HF. Now, HF when reacts or when is dissolved in water, it would give us H3O positive, that is hydronium ions, as well as fluoride ions. This acid is going to be in aqueous state. It would give us ions in aqueous state as well. Now, because this is a weak reaction, so not just this reaction would go in the forward direction, but this reaction would also start moving in the backward direction. So when a reaction happens in both directions, forward and reverse, it is said to achieve equilibrium. So we would see that weak acid dissociation would approach equilibrium. Now, if it approaches equilibrium, it can be defined with equilibrium constant as well. And equilibrium constant is the concentration of the products divided by the product of concentration of the reactants. We do not take any entity that is in liquid or solid state, so we would just take HF here. Now, because this is the equation for dissociation of an acid, therefore EQ can be replaced with A. So Ka specifically means that an acid has been dissociated into its ions, where one of the ions is hydronium ions. Therefore, Ka would be equal to hydronium ion concentration times fluoride ion concentration divided by hydrogen fluoride ion concentration. Now, always remember, if we have a strong acid, we would have a higher concentration of this. Like in this case, we have a strong acid that would give us more hydronium ions. Whereas if we have a weak acid, that would give us less hydronium ions because first of all, it will not break off completely, and because of equilibrium, the reaction is happening in the reverse direction as well. So these two would start combining to give us HF back again. Therefore, from here we can conclude higher the concentration of hydronium ions, stronger is the acid. Using this, we can write on our general Ka equation, and that is equal to hydronium ion concentration. Here, instead of F negative, we can take a general equation where HA reacts with water to give us H3O positive and A negative. Therefore, Ka would be equal to hydronium ion concentration multiplied by A negative over acid concentration. We would not take water because water is in liquid state. So this is our final Ka equation. Now, what is meant by percent dissociation? Percent dissociation is the ratio of concentration of ionized acid at equilibrium to the acid's initial concentration. How do we write it as a formula? Percent dissociation is equal to the concentration of dissociated acid divided by the concentration of initial acid. This ratio multiplied by 100 would give us percentage. Now, how would we determine what is the concentration of dissociated acid? That can be determined from this concentration of ions formed from the acid. Let's understand this from a question. Let's understand this from an example. So we're given a question where a student prepared a 0.10 moles per liter solution of C2H5COOH, that's propanoic acid. It is a weak monoprotic acid, and determine the pH to be 2.96. What is the acid dissociation constant for this acid? That means we're looking for Ka value. And what is the percent dissociation? Because we're looking for acid dissociation, we know acid dissociation of this is what we are going to get as a Ka value from its equation. So let's write this down in an equation form or a reaction form. We have C2H5COOH that reacts with water. State of acid is aqueous. Because it's a weak acid, it will undergo equilibrium. Would give us C2H5COO negative, because this H is going to be lost to H2O, giving us hydronium ion concentration. States of these are going to be aqueous. Now, since we have to calculate Ka, we need the concentration of both the products at equilibrium as well as the concentration of propanoic acid at equilibrium, because Ka is equal to the concentration of C2H5COO negative, this has to be at equilibrium, times the concentration of hydronium ion at equilibrium divided by the concentration of propanoic acid also at equilibrium. Let's see if we are given the equilibrium concentrations. When we go back to the question, we see that the student prepared this much concentration of propanoic acid. So this is going to be called the initial concentration of propanoic acid. This is not the equilibrium concentration. Therefore, we are not given equilibrium concentrations. If we are given initial concentrations, to go from initial concentrations to equilibrium concentrations, we have to make ice table. So this is the first thing we require to do this question. The second thing we have to remember here, because we are given the pH of this solution, then the pH would help find us the concentration of hydronium ions. And the hydronium ions concentration that we would get will be that of equilibrium concentration. So always remember, pH is going to give us hydronium ion concentrations at equilibrium. Therefore, we can use the pH value to calculate hydronium ion concentration at equilibrium to get this part of the equation. But for this and this, we will have to use ice table. So let's make an ice table for this. Initial concentration we are given is 0.10 moles per liter. We do not have to worry about the concentration of water because that is not going to be used in Ka formula. Initial concentration of propanoate ions is going to be equal to 0 because initially this has not been formed, and this initial concentration would be approximately equal to 0. Why is this so? Because hydronium ion concentration at 25 degrees Celsius is always from water going to be equal to 10 to the power negative 7, and 10 to the power negative 7 is a very small number that we can consider to be 0. Next change we would find out after we know this equation is balanced, and we notice that this equation is balanced. So this is going to be a minus x, this is going to be a plus x, and this is also going to be a plus x. At equilibrium, concentration is going to be 0.10 minus x. This is going to be x, and this is going to be just x as well. Therefore, Ka would be equal to x times x divided by 0.10 minus x, which is equal to x squared over 0.10 minus x. Since we have to find out the Ka value, we need to know what is this x, and we would find out this x using our pH, because pH is negative logarithm of hydronium ion concentration, and I told you earlier that in equilibrium pH would give us hydronium ion concentration at equilibrium. So we would be able to get the value of X once we isolate hydronium ion concentration from this formula. We're given the pH value as 2.96. So we would put here 2.96 equal to negative logarithm of hydronium ion concentration. And in the previous lesson, we learned how to solve for hydronium ion concentration. Basis 10, so it would be 10 to the power negative 2.96. That would be equal to hydronium ion concentration. When we put this on the calculator, we would be able to get the hydronium ion concentration as 1.1 times 10 to the power negative 3 moles per liter. Now this is the concentration of hydronium ions, and that is at equilibrium. Therefore, we can use this value as X, because hydronium ion concentration at equilibrium is X. So wherever we see X value in the Ka formula, we can substitute as 1.1 times 10 to the power negative 3. There is a square on X here, so there will be square here as well. We have 0.10 minus 1.1 times 10 to the power negative 3. When we put this all on the calculator, we get 1.2 times 10 to the power negative 5. And this is the value of Ka. Therefore, we have found out our Ka value. So this part of the question is done. Now we have to look for percent dissociation. We know the formula for percent dissociation is equal to concentration of dissociated acid, that is propanoic acid, divided by concentration of initial propanoic acid times 100. Now propanoic acid, when dissociates, would give us propanoate ion, that is C2H5COO negative, or we can say when it dissociates, it gives us hydronium ions too. Therefore, percent dissociation is the concentration of this formed at equilibrium divided by the initial concentration of the acid, which is equal to 1.1 times 10 to the power negative 3 divided by 0.10 times 100. When we put this on the calculator, we would be able to get percent dissociation, and that is equal to 1.1%. So this shows that propanoic acid just breaks down 1.1% to give us the product, and that shows how weak this acid is. And this is how we find the percent dissociation as well as the value of Ka. Now let's say we're given a question where 0.050 moles per liter solution of HNO2, that is nitrous acid, aqueous, is represented by the equation HNO2 plus water gives us NO2 negative plus hydronium ion concentration. We are asked to determine the pH of the solution. We learned in the previous example that pH is equal to negative logarithm of hydronium ion concentration at equilibrium. However, we are not given the equilibrium concentration of hydronium ions, but we are given the concentration of nitrous acid present initially in the solution. So we can use that to form our ice table. Let's rewrite on the equation. We have HNO2 aqueous reacts with water liquid to give us NO2 negative aqueous plus hydronium ion. Initial concentration of HNO2 that we have is 0.050. We do not have to worry about water liquid. This is 0 and this is approximately 0. Change would be minus X. Make sure the reaction is balanced, and this reaction is balanced. This is plus X. This is also plus X. Equilibrium concentration would be 0.050 minus X. Here we have X, and here also we have an X. Whenever we are given a question of this type, we would always be given the Ka value. So Ka value is known to us for HNO2, and that is equal to 5.6 times 10 to the power negative 4. So using the equation, we would write down Ka equal to the concentration of NO2 negative times the concentration of hydronium ions divided by the concentration of HNO2. This is X, this is also X, so we would have X times X divided by 0.050 minus X. Ka is given to us as 5.6 times 10 to the power negative 4. We have to solve for X because the value of X can be substituted here to give us equilibrium concentration of hydronium ions. To isolate for X, we'll move this over on the other side, and we get 5.6 times 10 to the power negative 4 multiplied by 0.050 minus X. that is equal to x squared. When we expand this, we would be able to get 2.8 times 10 to the power negative 5 minus 5.6 times 10 to the power negative 4x, and then we'll move this over. So we get minus x squared equal to 0. Now we can use quadratic formula to get the value of x, and quadratic formula is negative b plus minus square root b squared minus 4ac divided by 2a. We can rearrange the equation. So we would have negative x squared minus 5.6 times 10 to the power negative 4x plus 2.8 times 10 to the power negative 5, which is equal to 0. We have a as negative 1, b as negative 5.6 times 10 to the power negative 4, and c as 2.8 times 10 to the power negative 5. We would substitute these a, b, and c values in the quadratic formula to get x equal to negative b means negative and negative becomes positive. So we have 5.6 times 10 to the power negative 4 plus minus square root of 5.6 times 10 to the power negative 4 square minus 4. A is negative 1, C is 2.8 times 10 to the power negative 5 divided by 2, A is negative 1. When we put this all on the calculator, we would be able to get 5.6 times 10 to the power negative 4 plus minus 1.06 times 10 to the power of negative 2. The whole thing divided by negative 2. This would give us two values. One is negative 5.58 times 10 to the power negative 3, and the other value is 5.02 times 10 to the power of negative 3. Because x is supposed to be concentration and concentration cannot be negative, so we would discard this value and we would keep this as the value of x. Therefore, we know x is the concentration of hydronium ions at equilibrium, and then we can use this value to find out the pH. And the pH that we would get by substituting this in here is equal to 2.3. So this is how we determine pH once we are given Ka as well as the initial concentration of a weak acid.